My name is Tobias Overgaard, and I'll present some work which has been made in collaboration with my academic supervisor, Andreas Basse-O'Connor, and then a collaborator, Mette Skjødt. And I'm representing Denmark for this. Yeah. So let's just forget about this title and go ahead to the presentation. So I would like to present this problem from computer science. It's called the Boolean satisfiability problem. A quite well-known problem here. So the statement is we have m Boolean constraints, and when I say Boolean, I mean we have these two values, 0 or 1. We think about it false and true. So we have m constraints, and formally these are functions, and the goal is to have all functions evaluate to 1. So this we say that the constraints are satisfied in this case. So we are looking for an assignment. This is simply an input to these functions. So each of these variables, x1, x2, and so on, will be either true or false, or 0 or 1. And we want an assignment which satisfies all the constraints simultaneously. And so this is the problem. And of course, I mean, these could be any functions we want. So we look at disjunctive clauses, which means that each of these constraints will be, so this v here, this is logical OR. So it means that one of these variables must be set to true, and you are allowed to negate variables. So this is one example. You could have x1 or not x3 or x4 or x7. So we are saying that one of these 4 variables should be true. This x3, since it's negated, it needs to be false for the negated to be true. So I hope this problem makes sense. This is sort of the starting point for all of this. So this is an old problem. I will from now on use this notion of length of a clause, just means the number of variables that are being taken the disjunction over. Okay. So of course, if we want to have all of these satisfied, all the constraints satisfied at once, that's the same as saying that the conjunction should be satisfied. So if I take the logical and of all the constraints, I need to have this function f evaluate to 1. This is what I'm trying to do here. So I ask whether the pre-image here is empty or not. And I just give another example. It could be that there are 3 variables, and we have these 4 clauses. So the first 2 here have length 2, length 3, and then the last one is a length 1 clause. It's called a unit clause if it's only length 1. And this problem actually, even though it seems pretty simple, it's actually something that turns up in practice, and it's actually, so algorithms that solve this problem have actually been used a lot. So maybe for this audience, AI is the most interesting use where so especially for planning and scheduling, you could imagine if you need to schedule something, you could write it up as a constraint problem. But it's also used actually by Intel and other companies for their electronic design. It's used in bioinformatics and just in general for optimization problems. Okay, so we want to solve this problem, but the issue is that it's NP complete, which basically means that we don't know any fast algorithm that can solve the problem. So I'll just give an sort of to say, so if you have a good computer and you want to solve an instance of the Boolean satisfiability problem with 1,000 variables, this will take, according to the theory, up to 10 to the 97 years, and the universe is only 10 to the 10 years old, so this is not feasible, of course. So this is quite a shame. But in practice, many algorithms are solving these set instances with 1 million variables in only a few hours. So there's some discrepancy between the theory and what's happening in practice. And I guess you could say that this is sort of suggesting that this worst case analysis, I mean, this 10 to the 97 years, it's coming from an analysis where you're saying, what's the worst case? Like what's the, in the worst case, how long would it take? And this seems to be too strict of an analysis. So what do? The idea is for this analysis, you're sort of taking the maximum over all possible instances of the problem, and then you're looking at the computation time. But you could take the average instead. Maybe this would give you something more closer to the practice, what we're seeing. So that's what we'll do. We'll sort of introduce this probabilistic view. So now let's say that these clauses, we just choose them randomly, right? And we choose them independently, uniformly at random. And we just choose them uniformly from all clauses of length k with n variables. So there are 3 parameters here. So the length of the clauses, number of variables, number of clauses. So let me just sort of spell it out here. That means that each of these Cj, there will be a random function. So if I take an omega from the sample space, Cj of omega will be an entire function. So this could, for example, be this function, right? So Cj of omega evaluated at x could be this clause of length 4, which I also showed earlier. So now, taking the conjunction again, we get this. So I call this fk n comma m, right? So, and this is a random ksat instance, so I call it the random ksat model. And now I want to study the properties of this randomized version of the problem. And I think the most simple thing to consider is what is the probability that this Boolean satisfiability instance can be satisfied, right? So what is the probability that there exists this assignment that will have my Boolean formula evaluate to 1? It's a very simple question. And let's see what happens if we simulate. So we could try to simulate, basically generate a bunch of these formulas and see how often they are satisfiable. And obviously we'll have a small n here because, as I said, it takes a long time to compute these things, so we can't go too far. But we can do something, right? And it turns out, I mean, one can ask how many constraints should be chosen here. It turns out that the correct number is proportional to the number of variables. So if I take the number of constraints to be some positive number alpha times n, then this is what I will see. So the probability of set, so this is this event I talked about, that my randomly chosen formula is satisfiable. How will that look when I increase this number of constraints? Right, so of course it'll be a decreasing probability because with alpha, I'm increasing the number of constraints, so I'm making it more difficult to find a solution. So for n equal to 12, we get something like this. K is fixed here, so m and n are going to infinity. But if I keep simulating increasing n, there will be some pattern emerging here, and I hope you can see this. And one could then conjecture that what is happening, it seems that there's some cutoff point here where on the left side, the probability here seems to be converging towards 1, and on the other side here, the probability that we can satisfy the formula is converging towards 0. So this could be a conjecture, and it is a conjecture. So let's see. So it's written up here. So the conjecture is for each k, so there will exist this critical value alpha k, such that when I look at the probability of the randomly chosen formula being satisfiable, n variables, and then alpha n constraints, this will converge to either 1 or 0, depending on which side of this red line I'm on. Okay, so that's the conjecture. So it's only so k greater than 2, we'll talk about k equal to 1 later. But it has actually been proved for k equal to 2 the same year that it was conjectured. And here the critical value is 1. So from now on, I'll focus on this case that has been established, and I'll see what else we can do with this problem. So I hope this makes sense. So this red line is at the number 1 down here for the case k equal to 2. And remember, k is the length of the clauses. So this formula here, this could be a random 2 set instance, right, from this f2 function. And so these are 3 clauses of length 2. Let's just see what happens if I try to find a solution. So I could try to put x1 equal to 1, right? Set this equal to true. So I put in 1 here, but here x1 is negated, so it becomes a 0. Then this first clause is now satisfied. So 1 or something, this will always be true. But of course, this clause here, x3 or false, so x3 must be true for this clause to be satisfied. So x3 sort of now becomes a unit clause, right? It has to be set equal to true, and the last clause is unaffected. But now look here. I mean, if this conjunction is to be equal to 1 or true, then I have to set x3 equal to 1. This is sort of forced. So I do that, get a 1 here, but I get a 0 over here. So as you can see, this reduces to not x2. And now I'm forced to put x2 equal to 0 for this to be 1. But this does give me the satisfying assignment. X1 is true, x2 is false, and x3 is true. But notice that I only sort of chose one thing, everything else was forced. And the reason it's being forced is because these clauses of length 1 are appearing, and they're called unit clauses. So even though I'm looking at the problem for clauses of length 2, these clauses of length 1 start to appear, right? So I'd like to, so I just said again here, fk, this is the randomly sampled set instance, n variables, m clauses, length k. And this was the conjecture of the theorem now, right? So, okay, but so here's a theorem. I have my random 2 set formula. If I then add a number of 1 clauses, unit clauses, what will happen? Well, a theorem here from Belobas and a bunch of other authors states that if I add any polynomial in the logarithm of n 1 clauses, then this asymptotic probability of being satisfiable is unchanged, right? Because we see here the probability for just the pure 2 formula to be satisfied is 1 if alpha is smaller than 1, 0 if alpha is larger than 1. So of course it will remain 0 if I add more clauses. But if I only add this many 1 clauses or unit clauses, then for alpha smaller than 1, it will still be with high probability a satisfiable formula. So this is quite interesting. We can sort of ignore a number of 1 clauses when looking at the random 2 set problem. And what we did was we wanted to know how many 1 clauses can we ignore. I mean, this result has no statement of optimality here. So let's see what we can do. So here's how many more random 1 clauses can we keep adding before we reach critical mass? And here's the answer. So again, alpha smaller than 1. Now I'm adding, so we still have the 2 set formula here, random 2 set formula, and then we're adding a number of 1 clauses, and we're adding n to the qth power, and then with proportionality constant beta. So the statement is that the probability that this formula is satisfiable will be 1 if we're adding anything less than square root of n 1 clauses. And it will be 0 if we're adding anything more than square root n. But exactly at square root n, we get this probability here. So e to the minus beta squared, beta was the proportionality constant, divided by 4 times 1 minus alpha. Okay, so we can quantify exactly how many 1 clauses can be added before it sort of becomes too much, and the answer is a square root n. And maybe I can also mention here that this having this middle thing here, I mean q equal to a half, is actually a little bit extraordinary, because usually in such a thing, I mean, let's look at this example. We have no idea what happens at alpha equal to 1. This is called the critical point, and this is usually the most interesting case, but also the most difficult to analyze. And all we know is that this probability is bounded away from 0 and 1, but we don't actually know the value here. So as you can see, I sort of left out alpha equal to 1 because we don't know. But we actually could find here, so if we take q equal to a half, in this case, this is sort of the critical point here, we can actually give the exact probability or limiting probability here. Okay, and just for fun, I mean, we can take alpha to be 0, which means that now there are no 2 clauses, so we're just looking at the pure 1 set problem, which you saw was missing from the conjecture. But we see that the conjecture doesn't hold, because we need to, if we took alpha n 1 clauses, then the limit would be 0 always. But taking square root n, we get this smooth limit, like an analytical function, instead of this function which is 1 and then sort of cracks and becomes 0. So there's no sort of it's called a phase transition when this happens. But this is a smooth limit, and of course the conjecture doesn't hold for k equal to 1. Yeah. So that was actually I guess I don't know how much time I used here.
You have more time if you want, but
well, yeah, I guess we could just I mean chat and take questions. I have only could fit this many references, but this is the result for the 2 set with adding a polynomial amount and some other stuff, right? Yeah, so I guess we can just go to questions if anyone has any.
Yeah, thanks, Tobias. Perfect presentation. So do we have questions? Do you hear me? I switched to earphone because there's a storm here. Okay. So I have a question. So in these convergences, do you have any idea on the rate of the convergence? So it's a symptotic result here. Is it even interesting?
Well, I guess that would, I mean, that's a good question. I think it would be very interesting, because if let's say you wanted to sort of in practice, you had a problem and you wanted to say, we're almost sure this is satisfiable, because let's say we're down in this regime, then of course it would be super interesting to know how fast do we reach this this point. As far as I'm aware, there aren't any theoretical results, and as you can see, the conjecture was from 92, and actually we're still dealing with it for, let's say, k equal to 3, still an open problem. So this it's a difficult problem to crack, and I think rate of convergence would be very interesting and very nice to know, but it's not been established as far as I know.
Has anybody done some simulations, for example, in this direction?
Yeah, so there are simulations, but as I mentioned, if let's say we take k equal to 3 and we want to simulate what we find, these simulations take so long to do, because of this fact that the problem is NP complete. So it takes an exponential amount of time to solve these formulas. So it's hard to sort of get anything. The computer will run forever before you get your answers. So this is another issue that is sort of making it difficult.
It's very interesting. So thanks. Are there any other questions? Anybody? Okay. Okay, Andre, please.
Thanks. I hope others will also ask questions, despite I think the topic was quite difficult. One maybe stupid question. The result you showed holds for adding clauses of length 1. but maybe stupid, but closings of length 1 to a certain number of closes of length 2. What would happen if you would have perhaps 1 or more closes of length 3? Would something change significantly?
Yes, I think it's a great question, actually, and I I wish I knew the answer. The reason I chose length 2 was because sort of this base problem without anything extra has been solved exactly for the case k equal to 2. So if I wanted to do it for k equal to 3, then I would have to deal with both the original problem, which is unsolved, and then adding more. But I will say that in this small team that we have been doing some simulations and a little guesswork, and we do hope to present at some point results for length 3, as you said. I'll say 3 is the most interesting case, and then adding maybe clauses of length 1 and maybe also length 2, and I will say that's okay. There's something about this result, right? So, I mean, one could say that one could also ask what happens if we don't allow any contradictions in the one clauses, because somehow the one clauses, it amounts to saying that I want a solution, but I insist that, let's say, x1 is true and x3 is false. But if you are insisting that x1 is true and x1 should be false, then you are immediately done and cannot find a solution. And this is not very interesting. So you could ask what happens if you do not allow contradictions in the one clauses, and then you actually get the same asymptotics, but just a different probability here in the middle, but everything else stays the same, which is a bit surprising. But the reason is that when you have these one clauses, they sort of create new ones when you propagate them through the two clauses. But for three clauses, it takes 2 steps of propagation to get to a new one clause. And for that reason, it seems that the asymptotics here, the value of Q, actually changes whether you allow contradictions in the one clauses or not. So this is already a lot more complicated and interesting. I don't know if I should. Okay, I'll quickly mention that we're not too many here. So we think that the correct thing for Q here is actually something like 3/2. Something like that, or maybe I'm misremembering actually, but it's definitely not the same here. Yes, but I think it's a great question, and I think there's a lot to unpack. And if we're lucky, then maybe we could do an analysis of adding one clauses, get a result, and then maybe this could actually tell us something about the original problem that we didn't know beforehand. This would be the dream somehow.
Okay, thanks a lot. Thank you.
Yes. Well, thank you.
Great paper.